page 17 in your packet. Okay, so far, when we're dealing with volume, we've been rotating around an axis, whether it's this method or washer method. But we know that the results of the rotation is causing these circular-based objects to form. Right? But first, some definition here. Cross-section is the shape that results if we were to slice or cut the object in half and looking at the resulting shape. So here, if we were to slice this this bowl-shaped object in half, and you were to kind of open it up, you're going to see circular discs, right? Circular shapes. Same thing here. If I were to slice this in half and I were to open it up, I'm going to see circular rings, right? Circular rings. So the volume that we've covered so far have all involved rotating about the center around this axis that results in the circular area. So that's why we have this pi r squared or pi big R squared minus pi little r squared built into the integral formula, right? The antiderivative or the definite integral just allows us to accumulate this representative circular disk or rings from one end of the boundary to the other end. So what if we're not rotating though? What if we still started with the shaded region, but instead of rotating, we let it be the base of a three-dimensional object? Okay. So now we're going to be building these cross-section areas on top of this base. So no longer are we going to be rotating around an axis. We're going to be creating these kind of volumes of these odd-looking objects. Okay. Now we never have to worry about what these objects look like. Just have to kind of conceptually understand what we're creating as we're building. So, for instance, let's look at this quarter circle, right? This is kind of drawn in a three-dimensional surface. We're going to do everything two-dimensionally, but just for now, just kind of giving you a visual perspective. Let's say we want to build differently shaped squares on top of this base. This is what it would look like from one end to the other end. So you can kind of see that, you know, depending on the distance from the axis to the curve, that's going to dictate how large the square is going to be. So if we're over here in the corner, that distance is very short, so we're going to have very, very small squares. But as we increment from one end to the other end, we're going to create, it's going to be kind of like this kind of odd looking object. But the consistent thing here is that if we were to slice it, doesn't matter where we slice it, over here or over here, if you open it up, you're going to see consistently squares for every cross section that you open up. So there's different shapes that we can create. We can either build squares, we can build right triangle with leg on the base, isosceles right triangle with hypotenuse on the base, rectangles, equilateral triangles, semicircles. So just depending on what we want to build, we can just insert the information into the formula. Okay. Now the information that we're going to gather is going to feel very similar to what we did with area and volume by disk and volume by washer method. We're still going to draw that distance from one boundary to the other. It could be either vertical, it could be horizontal. Vertical is just like before, it's going to be easier because everything is in terms of x. Horizontal is going to be a little bit more involved because we have to rewrite the equation. But we find the bounds the same way. If it's top minus bottom, we look for the left and right endpoint in terms of x. If it's horizontal base, then everything's in terms of y, and we want to look at bounds from the lowest to highest y values. Okay, so, but all we're going to do is we're just going to get just the bare minimal information on that we have to draw out, and the rest of it we just convert it to a formula. We're never going to have to worry about exactly what these shapes look like, just have to gather enough information to put it into the formula. Okay, so let's start with example 1. Now for example 1, we're going to find the volume of this object that we see here. Okay, that's what we're going to do. So example 1 here. Find the volume of a solid if the base is bounded by the curve of y equals square root of 1 minus x squared. That's going to be the quarter circle. Okay, so here's our two-dimensional version of this shaded region here. There's my square root of 1 minus x squared. Bounded by the curve, the line y equals 0, and the line x equals 0, basically the first quadrant. And there's our shaded region. Okay, we're no longer going to be rotating, so there's no axis of revolution, but instead, you're going to be told explicitly exactly how and where to draw your rectangular base. Okay, and we're going to be building squares. Okay, so we know we're using the square formula here, parallel to the x-axis. So you're always going to be told exactly how to draw your base length. Okay, so parallel to the y-axis, let's think about what that means. Y-axis is which direction? Vertical, right? So parallel to it means same direction, right? So there's our vertical base. Okay, from a three-dimensional perspective, is this. All right, we're building squares with this being a representative base, right? Sorry, I didn't draw that correctly, but essentially we're building squares out of the page. That's going to form these shapes here. Okay, so we see a vertical base. So we'll do top minus bottom, just like how we would if it was disk or washer method or area formula. So let's go ahead and find that distance. But now this doesn't represent the height of a rectangle or the radius of a circle. Now this represents the base of a particular shape that we're trying to, or a dimension of a particular shape that we're trying to build. I'm just going to call it base. Okay, so top minus bottom. What's the top of this this rectangular base touching here? Okay, the square root of 1 minus x squared. Okay, what's the bottom of this base length? 0. So that's y equals 0. Okay, so that cleans up to be just square root of 1 minus x squared. So now that we have our base, we have to be able to use, we want to start building the shape that we want to build, right? So we're building squares. So the squares has a formula of base quantity squared. So I'm just going to look at my formula above, take my base, insert it into the formula. So area equals base squared. Now this only gives us the area of one representative square, okay? But we want to accumulate all these squares from one end to the other. So now we're going to insert into our volume formula. So volume formula, we just take that area component, insert it in here, and the integral is going to accumulate from one end to the other. Before, the area of a cross section were circles. So before it was pi r squared or pi little r squared. That was for disk and washer method. But now we're going to be inserting area of different shapes in this space. So depth integral from one end to the other. We're stacking these squares from one end to the other. So this is x value of 0. What's the x value here? Okay, we can use our graphing calculator, or we can solve this out by hand, right? This is just the intersection of the curve and the x-axis. If I set them equal to each other, right, square both sides. Okay, -1 is going to be on the other side of the semicircle, but +1 will be the one that makes sense for us. Okay, insert the area component into your integral notation. You can drop the square root in the square if you want, but either way, you can enter into the calculator. Now, notice something that is missing that we are used to seeing. What's that? Pi, right? But why is there no pi here? Because this isn't a what? It's not a circle, right? This is not circle based. This is not rotation based. So there's no need for pi. Now, there is one cross-section formula that has pi in it, and that's a semicircle. The semicircle has, we're not rotating, but we're building semicircles. So semicircles is based off of a circle, so that's why there's pi. But usually, we're not going to do pi r squared like we would with this for washer. Okay, enter into our calculator, volume equals 2/3. We don't attach pi, just cubic units. Okay, so we spent so much time with area and disk and washer. This should just feel like a slight extension from what we've already built up to this point, right? You're still drawing a rectangular distance. If it's top minus bottom, you would find that length the same way. If it's right minus left, you would rewrite the equation. The boundary, you find the same way. The only thing different is that you're inserting that length into a different formula. But other than that, everything else feels the same, right? You're still finding the length the same way. You're still finding the bounds the same way. Okay, so just a slight adjustments. This base that we're finding is how we found the radius from before, but we're inserting into a different formula. Okay, any questions so far? Okay, all right, back page 18. Right. I'll put the formulas above for easy reference. Example 2, find the volume of a solid if the base is bounded by the curve y equals x squared and y equals 4. So let's go ahead and graph that. That's a parabola and the horizontal line. Thank you. Okay, there's our shaded region. Cross sections are isosceles right triangles whose hypotenuse lie on the base. So there's a formula for that. That's the 1/4 base squared. And you're told exactly how to draw that base length parallel to the x-axis. Okay, so which direction is that? Okay, so x-axis is this way. Parallel, so same direction. Horizontal. So anytime you see something horizontal, what do we have to be aware of? Yeah, the equation is not going to be in the correct form. You always have to rewrite the equation. Okay, so we'll deal with that y equals x squared. If I want to solve for x, what do we get? But in this case, there's a what? If I take the square root, what's going to pop up? Plus or minus square root of y. And now the negative square root of y will play a role here because now we have both sides of the parabola showing up. So we have the positive square root of y, which is on the positive side here. And then we also have x equals negative square root of y, and that's over on this side. Okay, so we'll do right minus left. Right endpoint of my base length is touching the root y. Minus the left endpoint is touching negative root y. What's that going to equal to? That's root y minus negative root y. 2 root y. Okay, let's find the appropriate area formula. Isosceles right triangle with hypotenuse on the base. So 1/4 base squared. Now we can enter this directly into the integral formula, but the more that we can clean up, the less that we have to type into the calculator, right? So I'm just going to clean this up here. I'm going to square both the 2 and the root y. And that cleans up all the way to just be y. Okay, so now that's my area. That's my area expression. I'm going to insert into my right minus left. So that y will get inserted in here, and I just have to worry about the bounds. Okay, my bounds are in terms of y. Okay, and we're stacking these right triangles out of the page from down here all the way to up here. So what are my bounds going to be? What's the lowest y value? Okay, what's the highest y value? 4, right? So from 0 to 4. Okay, you can use your calculator, but this is easy enough to just do it by hand, I think, using power rule. 16/2 is 8. Again, there's no rotation going on here. There's no circle involved. We've not 8 pi, it's just 8. And imagine triangle sticking out of the page. It's just going to be an odd looking object. We're not going to worry about what the shape is. Just be able to pull the information and get into and find the volume value for it. Okay, any questions with 2? Okay, try example 3. Same base, same shaded region. See if you're able to use example 2 to help you do number 3. Okay, same shader region. We're building a different shape, semicircles, but that comes later. Let's figure out how to draw the base. Okay, base is now perpendicular to the y-axis. Which direction is that? Okay, let's think about that. So y-axis is this direction, right? So perpendicular to it would be horizontal. So just be aware that there are 4 different ways that you can say horizontal, vertical. You can say parallel or perpendicular to the x-axis. You can also say perpendicular or parallel to the y-axis. So just take your time, read it carefully, and create, visualize it so you don't accidentally draw it in the wrong direction. So really, it's going to be the same base, right? Same base as before, same bounds, just a different area formula. Base is still 2 root y, bounds is still from 0 to 4. But now I'm inserting it into a different area formula. I'm looking for the semicircle formula, which is pi over 8 base squared. So pi over 8, 2 root y squared. Do a little bit of cleanup so I don't have to do as much work in the calculator. Pi over 2y is the area. Pi over 2 is just a coefficient. So if I just took that pi over 2 out, and it's just an easy integral, I can do this by hand if I wanted to, and just get it down all the way to 8, and then take the 8, multiply by pi over 2, and we get 4 pi. Here, we are going to have pi show up, not because there's rotation going on, but because there's a semicircle that we're building on top of this base, and semicircle is coming from the area formula. Okay, any questions with 3? Okay, take a look at number 4. Let region R be the area enclosed by the function natural log of x and 1/2 x minus 1. So there's a curve and a line. Region R is the base of a solid, such that each cross section perpendicular to the x-axis is an isosceles right triangle. So we're told what formula that we're going to be inserting into. But let's draw the base first, right? Base is perpendicular to the x-axis. Which direction is that? Yeah, x-axis is horizontal. Right? Perpendicular to horizontal is going to be vertical. So this will be top minus bottom. If you see a vertical base or vertical rectangle or vertical radius, you know that you're going to have an easier time setting up your expression, right? Everything that's given to you is ready for you to use. So find your base, insert it into the correct area formula, and then we also need to find what? Bounds. Okay, so bounds, you can set the equations equal, but it looks like it's going to be hard to do this by hand. So using your calculator, practice using numsolve. You may have to do two different starting points, right? One starting point at 0, another starting point on the other side, because if you do numsolve, it's only going to find the closest value to that starting point. But if you're using your graphing calculator, practice to see if you can do your intersect, right? Graphing the 2 graphs, zooming in, identifying the 2 points, find the intersection. Okay, I'll come around and help you if you're needs some support with your calculator, and then I'll show the answer after you guys have a chance to try it. Here, if you solve again, now let me start closer to this. Top minus bottom is going to be your base, and then you're going to insert into the formula for isosceles right triangle. Careful that when you are building your base, that you're starting off with parentheses around the bottom, right? So that you don't forget to distribute that negative through the parentheses, right? So this is, you gotta be careful here, right? If you don't have parentheses there, chances are you may forget to distribute that negative through, and that's going to throw off your answer. And let me know if you have any trouble with your calculator, finding the intersection, graphing, zooming in. Okay. But hopefully you guys find this to be just a slight extension from disk and washer method, right? We're not doing pi r squared, but we're just inserting into a slightly different formula, where you're still finding the base length the same way, you're still adjusting the equation the same way, you're still finding the balance the same way. It's just that the step from base to area is what's different, right? Once you find that base length, you're going to insert into whatever area formula that is asking for you to build. any questions? Okay, so we're going to spend the rest of our time going back and just reviewing disk and washer method, especially identifying between those two and drawing our radius correctly. So you guys just picked up the handouts with the key for that worksheet on my chair there. So go ahead and have that out. Anybody still need this page? So I copy and pasted the same diagram over and over again, but we have 3 different regions, and we're going to be rotating around different regions. So we're going to have a lot of different opportunities to try different problems. The second, or starting with the second graph, it kind of got a little blurry. So if you guys can kind of fill those in. R1 is this triangle that's with the hypotenuse that's at the y equals x. Region 2 is this region between the curve and the y equals x. And region 3 is this triangle kind of looking shape with that curve there. So there's R1, there's R2, and R3. And then each problem is going to tell you rotating a shaded region, or identify the shaded region for you, and telling you that you're rotating about either a vertical or horizontal line. And from there, we have to decide, are we working with this method or washer method? Is it top minus bottom? Is it right minus left? Okay. Okay, so to start off, the first one here, region R1 is this upper triangle. Okay, you're rotating about x equals 0, so there's your dotted line. Okay, first decision we have to make, is this disk method or is it washer method? This method, because that dotted line is up against the flat surface of this blue region, right? It's touching every part of that blue region. If it's only touching on one point because it's a curve, then it's gonna be washer method. Or if you see any sort of a gap, it's gonna be washer method. But you see the flat surface with that dotted line, it's going to be this method. Okay. And we know that our radius has to be perpendicular, so it has to be horizontal. So anytime you see a horizontal radius, you got to do what? Yeah, you got to rewrite the equation. In this case, it's not a big deal because the only line that graph is touching is y equals x. So if you just rearrange it, that's just x equals y. And then also think about the bounds as well, right? You're stacking these circular disks from the lowest y value to the highest y value. Okay, so try that. You have the key attached, so you can kind of check your work. And we'll just kind of have you guys go through as much as you can in the remaining 15 minutes or so, and I'll come around and just see how you guys do. I want to have you try it so I can see where you're. Yeah. Now we'll do zoom 6, just so I can get at least 2 of them. Yeah, zoom 6. That's standard. And then infinite larger box. Zoom 1. Yeah, so you're going to see you're going to draw the box first, and then you're going to hit it. Yeah, now don't hit enter again until you have a box showing. So go down. There you go, draw the box first. So now you're going to do intercept, second case. Second case. Let's get it out. Okay.
Just do those two sections. Okay.
So if you're ever in trouble where you can't see the graph, you can always go to zoom 6 and it'll take you back to the negative. Does everybody have the key to check their answer with? I just want you guys to become more comfortable. Any shader region, any axis, you can instantly tell whether it's going to be disk or washer, is it top minus bottom, right minus left, and be able to create your expression, but then also be able to find your balance. Oh, intersection. Yeah, so that's it.
Yeah.
let me know if you're having trouble with your calculator. You know, see if it's not going to be out there. Really graph it. You know, to see it. Right, so right left, which means that every equation you gotta use is in this is the what is the y-axis. Y-axis has the equation that's supposed to this line has the equation x equals this. So if you do right minus left, it's like 1 minus 0. So it's the right hand point is touching the 1, left hand point is touching 0. The right minus left, right hand point is touching the 1, and left hand point is touching 0.
Got a weird number.
Which one is this? So you know you have to get it in terms of x equals. So we get x equals x is equals to square root of the x, which is fine. Okay, this is not touching this is touching the line. So the line is touching x, so it's just going to be x and y. So basically the curve is not part of the shaded region, so you're not going to involve the square.
Is this one? I scribbled.
Yeah, so the only time you're going to deal with the word of square is as far as what goes into.